For this lesson, as the start of our new unit looking at exponential functions, I thought it would be useful to review exponent laws. There are probably quite a few students who are familiar with some or all of these exponent laws, so I'm going to be going through quite a few of them. It may result in a bit of a longish video, so you might have to jump around if you're looking for a refresher on something specific. Let's start right at the beginning talking about when we talk about a power. So in this case, a power, it's a product of identical factors, and it's made up of two parts, the base and the exponent. What this is essentially saying is I have my base is 2, and to the exponent 3 means that I need to take that 2 and multiply it by itself 3 times, which of course in this case gives us the answer of 8. So we end up with questions like this. Very simple. These are just evaluate. You could evaluate these on your calculator, of course, but it's very important that you know what they're supposed to look like algebraically. Something is not working here. Let's try that again. There we go. It's important that you know what these look like algebraically, because once we start working with variables, you're not going to be able to go to your calculator for that. So 3 times 3 times 3 in this case is equal to 27. Now there's an important distinction here. We've got negative 3 to the power 3, or to the exponent 3. So because that negative 3 is in the bracket, that means that negative 3 is the base. So whether we do this in our head or whether we write it out like this, we actually need to write it out this way. Negative times negative times a negative gives me a negative, and then 3 times 3 times 3 is what we had before. 27, this one gives us negative 27. What about negative 2 to the power 4? In this case, the negative sign is not part of the base. In this case, my base is equal to 2. So this is actually negative bracket 2 to the 4, where 2 is the base, which is negative, and of course, I'm not going to always write these things out, but it's 2 multiplied by itself 4 times, so that's negative, and then this answer is actually going to give us 16. The same thing works with fractions. So with fractions, we can write this as 4/3 times 4/3. That's one way to do it, which we'll evaluate to 4 times 4 gives us 16, 3 times 3 gives us 9. Or we could have gone to here where we said that's the same as 4 squared over 3 squared. So you have a couple of options on how you interpret this, but of course we end up in the same place. 4 squared is equal to 16, 3 squared is equal to 9. All right, let's start to get into some algebraic operations. What happens when I am multiplying two different powers together that have the same base? So in this case, the base is 3. One of them has an exponent 1, one of them has an exponent 2. Well, the first thing I'm going to do is I'm just going to actually write this out. 3 to the 1 is 3. 3 to the 2 means multiply 3 together twice, and we end up with 3 to the power. We have 3 of them, which gives us an answer of 27. But 27 is actually 3 to the power 3. That's 3 3's multiplied together. So we end up with this rule. If we have the same base and exponents x and y, then we keep the same base and we add the exponents together. We end up with a similar rule for division. In this case, I have 3 to the 1 divided by 3 to the 2. And it's actually, I'm going to change this example on the fly. I'm going to change this to 3 to the 2 divided by 3 to the 1. And you'll see in a moment why I've chosen to do it this way. 3 to the 2 is 3 times 3. Divided by 3 to the 1 is just 3. The 3's divide out and become 1, so I end up with a final answer of 3, but 3 is just the same as 3 to the 1. So what we actually did there was this exponent 2 minus 1. 3 to the 1 is the same as 3 to the power 2 minus 1. And that is our rule for division. So if I have a to the x divided by a to the y, which is the same thing as writing it as a ratio or a fraction, a to the x over a to the y, I keep the base a, and then I subtract the second exponent from the first. We also have a standard restriction here. Because I have a base a in the denominator, that value of a is not allowed to be 0 because that would result in a division by 0. Okay, what about a power of a power? Here I have 3 to the power 2, but then that whole expression is to the power 4. So I could rewrite that as 3 to the power 2, 3 to the power 2, 3 to the power 2, and 3 to the power 2, because I've got 4 of them. That's what this outer exponent means. But now we can make use of one of our previous exponent laws, which is I'm going to keep the same base, but I'm going to add all of these exponents together, and I end up with 3 to the power 8. But where else could that 8 have come from? That's the same as 2 times 4. So that's 3 to the power 8 is the same as 3 to the power 2 times 4. So the rule is the base to the power x to the power y is the same as keeping that same base and just multiplying those two exponents together. So some practice to make use of those. If you're looking at this, you might want to pause here, take a look at the screen, try to work these out on paper yourself. 4 to the power negative 6 times 4 to the power 4. That's the same as 4 to the negative 6 plus 4. I add the exponents together, so that gives me 4 to the negative 2. Up in a future slide in this lesson, but upcoming, we're going to talk about negative exponents. So if you're not comfortable with that right now, just leave it in this form, and that's what I'm going to do for now. This next one, I have a fraction, so my base is negative 3. I use the exponent from the numerator minus the exponent from the denominator, and I end up with 2 minus negative 3, which is negative 3. 2 minus negative 3 is to the 5. And I'm really only interested here in writing things in terms of a base and an exponent, so I'm not going to convert these into numbers. 5 to the negative 2 multiplied by 5 to the 4, all to the negative 2. So I'm going to take care of what's inside this bracket first, following order of operations. That's 5 to the negative 2 plus 4, and then that's all to the negative 2. 5 to the negative 2 plus 4 is just 5 to the 2, and that's all to the negative 2. And now I multiply these exponents together, and I end up with 5 to the negative 4. This last one, a little bit trickier. First of all, it doesn't just have numbers that we can resolve. We've got some variables here. The first thing I need to do is follow order of operations, so I need to take care of what's inside the brackets first. But if you take a careful look at this, you'll notice there's nothing else that can happen inside these brackets. There are no numbers inside here for the 3 to multiply or add with. A squared is as simple as it can be, and so is b. So now that I've done that, what I really have here is simply all of, since there's no exponent on either of these brackets, it's just all of these terms, or all of these factors, multiplied together. And if I think of it that way, there is a property in mathematics called the commutative property. If I could spell it would help. Commutative. So the commutative property says that when you have multiplication of all factors, you can just move those around. The commutative property is the reason why 2 times 3 times 4 is the same as 4 times 2 times 3. I can move that around and I don't change the value. So if that's the case, then what I can do mentally is think, okay, well, I'm going to multiply these numbers together. I'm just like bringing this 2 out here. 3 times negative 2 is negative 6. A squared times a cubed, I add those exponents and I end up with a to the 5th. B to the 1, we don't write an exponent of 1, but that's understood to be b to the power 1, times b to the 4 gives us b to the power 5. Now, speaking of the exponent 1, so what happens when we have an exponent of 1? The rule is that we don't change the value. So a to the power 1 is simply equal to a. Anything raised to the power 1 is just that thing. All right, let's take a look at some ideas about patterns. So we just said anything raised to the 1 is that thing. So 2 to the 1 is equal to 2. 2 squared would be 2 times 2. That's equal to 4. 2 cubed is 2 times 2 times 2 is equal to 8. In this case, to move up, each time I'm moving up, I'm multiplying by 2. I'm multiplying by 2. In that case, you could also start at 8, and you could say moving down is divide by 2. Move down is divide by 2. So that means that I should be able to apply that pattern. In particular, we're interested in this. What about 2 to the power 0? So 8 divided by 2 is 4, divided by 2 is 2, and so if I go this way and divide by 2, that's equal to 1. And this would have worked even if I had done, let's say, 5 to the power 3, 5 to the power 2, 5 to the power 1, and 5 to the 0. 5 to the 1 is 5, 25, 125, and then going the other way, divide by 5, and this last one, divide by 5, gives me 1. So anything to the power 0 is going to give me 1. 8 divided by 2 gives me 4, divided by 2 gives me 2, divided by 2 gives me 1. I could do that for any number I want. So we end up with this rule, which is that anything to the power 0 is equal to 1. A cannot be 0, and the reason is because 0 to the 0 is undefined. Mathematically, there are actually multiple schools of thought on what this might mean, but it's not, to my knowledge, as yet, it is not completely resolved, and so 0 to the 0 is considered to be an undefined quantity. All right, let's continue that patterning. 8 divided by 2, divided by 2, divided by 2. So that means if I get into negative exponents, what is 1 divided by 2? Well, you might want to write that as 0.5 as your first instinct, but we can actually do better than that in a more useful way. 0.5 is the same as 1/2, and in particular, 1/2 is the same as 1 over 2 to the power 1. Let's divide by 2 again. So I don't want to do this decimal root, but let's take this and divide by 2. What's 1/2? 1/2 divided by 2 is the same as 1/2 multiplied by another half, and that's equal to 1/4. So this one gives me 1/4. But can I write 1/4 in terms of exponents? Yes, that's actually 1 over 2 squared. Divide this by 2 again, gives me 1/8, but 1/8 is actually 1 over 2 cubed. So you can see, for example, 2 to the negative 3 is exactly the same as 1 over 2 to the positive 3. So we see this effect with a negative exponent. We can rewrite this with a positive exponent where we move between numerator and denominator. So 2 to the 0 was 1. Divide by 2 is 1/2. Divide by 2 is 1/4. But that's also the same as 1 over 2 to the 1, 1 over 2 to the 2. And so any exponential like this, a to the negative x, can be written as 1 over a to the x, And that's the same as 1 over a to the x written this way. So this is 1 over a all to the x. That also works as well. Now, distributive rule for powers. Sometimes we don't want to have to write all of this out first. So for example, I've got 7 squared times 2 to the 5th. I'm really focusing on powers here, so I'm not going to write 7 squared as 49, and I'm not going to write 2 to the 5th as 32. I'm just going to leave it this way. I've got this whole thing cubed. So the definition of this means this entire set of brackets 3 times. So 7 squared times 2 to the 5th, 7 squared times 2 to the 5th, 7 squared times 2 to the 5th. Now all we have is multiplication of factors. 7 squared times 7 squared times 7 squared is 7 to the 6th. 2 to the 5th times 2 to the 5th times 2 to the 5th is 2 to the 15. Now let's go back and take a look at what we had here. We know that there is a rule about multiplying when you have exponent to an exponent multiplying. So take a look at the results we have here. 2 times 3 gives me 6. 5 times 3 gives me 15. So I actually could have gone from here to an answer of 7 squared to the 3 times 2 to the 5 to the 3. And this is known as the distributive rule for powers with different bases. Here I had a base of 7 and a base of 2. The same thing will work here with this fraction. So 7 to the 2 over 2 to the 5, all to the power 3, can be written as 7 to the 2 to the power 3 over 2 to the 5 to the power 3. 7 to the 2 to the 3 is 7 to the 6. 2 to the 5 to the 3 is 2 to the 15. So here is our more simple rule when the exponents of a and b are 1. ab to the power x, all to the power x, is a to the x times b to the x. A over b, all to the power x, we can change to a to the x divided by b to the x. If we have something more complicated here, where the exponents are not 1, then a to the m times b to the n, all raised to the power p, I'm going to actually use the a to the m to the power p, b to the n to the power p, and now that's a to the power mp, b to the power np. Similarly, with this fraction, move that down a bit, this one is going to be a to the power mp, all divided by b to the power np, doing that in one step this time. So applying these things, now it says, same as a question we did before, except for now it wants positive exponents. So this first one is actually what we did before. 4 to the negative 6 times 4 to the 4 is 4 to the negative 2, adding those two exponents together. But that's equal to 1 over 4 to the positive 2. Five to the negative 2 times 5 to the 4 is 5 to the 2. All to the negative 2 is 5 to the negative 4. And the alternate form for this is I could write this as 1 over 5 all to the positive 4 if I wanted to. I still actually prefer, in the end, since 1 to the 4 over 5 to the 4, well, what is 1 to the power 4? That's 1 times 1 times 1 times 1. So we don't actually need to put the exponent there for that one. Now, how about no numbers? X to the negative 3, y to the 5, all to the negative 3. So that's going to be x to the negative 3 to the negative 3, y to the 5 to the negative 3. X to the negative 3 to the negative 3 is x to the positive 9. y to the negative 15, but we want positive exponents, so that's x to the positive 9 times 1 over y to the positive 15. And if you had gone straight to this, which is my preferred representation, that of course would have been fine. So going straight to there is perfectly good. This first bracket needs to be resolved, and there's actually something here that's pretty easy to trip over, which is you need to remember that that is the number -1 multiplied by a to the 5th times b. So there's a few ways you might want to deal with this. You might want to do each of these factors one at a time. So you could write this as -1 to the -2, a to the 5th to the -2, b to the -2, -1 to the +2, a to the +2, b to the -2 to the +2. Now we take a look, simplifying further. Well, I actually have a -1 to the -2 and a -1 to the +2. So that gives me a -1. -2 plus 2 is just equal to 0. A to the 5th to the -2 is a to the -10. B to the -2, I'm just going to rewrite that as b to the -2. A to the 2, I'm going to write that as a squared. And b to the -2 to the -2 gives me b to the -4. And now that I've done that, I've simplified things. There are no brackets. We have no exponents to other exponents, no powers to other powers. -1 to the 0, anything to the 0 is just equal to 1. A to the -10, a to the +2, that gives me a to the -8. B to the -2, b to the -4 gives me b to the -6. So this ends up being 1 over a to the +8, b to the +6. So here I say the exponent laws also work if you have polynomials instead of numbers. So this is the first example we had where the exponents themselves are not numbers, but it will still work. This first one is a power to a power, so that means we multiply the exponent times the other exponent. So that becomes x to the exponent 2a plus 4. And I'm going to expand that. 3 times 2a is 6a. 3 times +4 is 12. Make sure you are careful with your writing or use brackets. If you're not very good at scaling your text or keeping things on a straight line, you need to indicate that this is the exponent and that this is the base. Here I have x as my base. I'm multiplying 2 powers of x. So I'm going to rewrite my base and I'm going to add the exponents. You don't have to do this step. I'm just writing it out to make it very clear. So a plus 3a is 4a. Positive 5 plus 1 is 6. So that's 4a plus 6. For this next one, I have division. And so I'm going to be subtracting exponents with a common base. 4m minus 3n. And from that, we're going to subtract m plus 5n. 4m minus m is 3m. Negative 3n minus 5n is minus 8n. There are a couple of ways you could do this one. I would recommend that you just get everything looking like powers of x. So this first term I'm going to leave alone. That's x to the power y. This one, this middle term, middle factor I should say, x to the y plus 1 all to the y plus 2. That means I have to multiply those exponents and I end up with x to the y plus 1 times y plus 2. And I'm going to use a property that we looked at before in reverse. This is 1 over x, which is the same as writing this as x. And now I'm going to change a positive exponent into a negative exponent. You won't do this often, but sometimes it can be very useful. In this case, that means I now have everything in terms of powers of x multiplied together. So now I can write my single power of x, and all I have to do is add these exponents. So I'm going to have y plus, I might as well just go ahead and expand this. Y plus 1 times y plus 2 is y squared plus 3y plus 2, and then minus 6y, because we're adding this negative 6y. So minus 6y. And now simplifying that exponent, y, let's see, we've got a y squared. There's only one of them. Y plus 3y is 4y. Minus 6y is minus 2y, and plus 2. And once again, I'm just going to remind you how important it is that it's very clear between what's the base and what's the exponent. So just a summary. Here are the exponent laws that we went through when we have the same base, or a couple of generic exponent laws where there's only one base with a couple of things happening. And then here is a summary of the exponent laws when you have different bases. So when you have powers that involve different bases, different numbers, that sort of thing. Okay, so that's it for this lesson. Hopefully that was largely review for people.